right, welcome back. We're going to continue our review of pre-calculus limits. So we're basically covering everything you learned last year in limits in about a day here. So let's review the algebraic ways now to look at limits. One of the easiest methods to check if a limit exists is to see if the value exists. So we're basically right here using what's called the substitution method. And what we're going to assume is continuity. You might recall in a previous video, the last video, we talked about continuity. And we said something is continuous if the limit and the value are the same. And that's what we're going to try to show here. If we show that the value exists at a point, then it has to be continuous at that, then the limit must also exist at that point too. Now notice we're not looking at it graphically. We are looking at these using functions this time. So let's take a look at example like number 1 right here. We want to see what is happening to the value of the function as x approaches 3. So now we're going to do this a new way. In last year, you would just plug it into the top and into the bottom, but I want us to get us ready for the AP test. For the AP test, this is what we're going to do. So this is new. It's just a different way to do it. We are just going to take the value at 3 of the top. 2 times 3. Whoops. As a matter of fact, we're not going to do the value. We're going to do something even better. That's not deleting it. There's my eraser. There we go. The best way to do it, there we go, for calculus is to do this. Take the limit as x approaches 3 of the top. 2x minus 5. And if we did that, plug in a 3, we would get 6 minus 5, which is 1. And do the same thing for the bottom. X plus 1, and that's going to give us 4. So notice, we actually get a number. So therefore, well, the top was 1, the bottom was 4. Therefore, there's our limit, equals 1/4. And we can do the same thing here. If we just plug in here. Now the first way is going to be a little bit weird for us to get ready to do, but it's just getting us ready for the AP. Now, for example 2, of course, there is no really weird one right here. There's no fraction, so we can just directly plug in, and negative 1 squared is 1, minus 3 times negative 1, minus 4, and that gives us 0. So we're approaching 0. Now notice again, we're assuming continuity. Because I got a value, the value exists, and the limit exists. Therefore, we would say that this would be considered continuous. And that's all we're really kind of doing right here. All right, now this is the part that keeps me up all night. What is the sine of pi over 3? Okay, sine of pi over 3 is, what is that, root 3 over 2? There it is. Limit. So the easiest way to do it is just to literally just plug it in. But then we get something called that indeterminate form, which you might recall in my first video on this lesson here. When substitution fails, we get sometimes what's called the indeterminate form. Now, if we try substitution method and we get either 0 over 0, now danger, we do not write this ever. The AP will not give you any points, and you can lose up to 3 points for that silly mistake. Now, I'm going to be honest with you, pretty much everybody writes it. But for the AP, you cannot, and there's a reason for it. We'll talk about that later on, okay? And I'll show you in this video about why we really don't like to write 0, 0, or infinity, infinity. But now remember, we talked about this in an earlier video. This is a huge problem because we don't know their values. That's why they're called indeterminate. Now, there are other forms. We'll talk about those at a later date. If we get 0 over 0 or infinity over infinity, we have to use another method. And we're going to talk about those. And you saw these last year in your pre-calc course. But danger, do not, have I said this yet? Do not write that. So the first technique is what we call factor cancel. In factor cancel, we're going to use algebra to cancel out a common factor. In Algebra 2 and Pre-Calc, we use this to find the whole of a rational function. So you actually saw these. You actually did this. This is how you found the whole in a rational function. So for example number 1, what we're going to do is we are going to try this. So I'm going to write this out. Remember, we're doing this for Pre-Calc. We're going to take the limit as x approaches 4 of the top, x squared minus x minus 12 If you plug 4 in there, we do get 0. You can verify that. Looking at the bottom, as x approaches 4, x minus 4, that's also 0. So what I can do now is I can factor the top. I get the limit as x approaches 4, factoring the top, x minus 4, x plus 3 over x minus 4. Those cancel. And then I can plug in the 4. Whoops, those canceled out. If I plug in the 4, we now get 4 plus 3, which is 7. And that is our limit. This is what we are approaching. Now remember, this is 0 over 0. So that's telling me it's indeterminate, but if I factored it out, I canceled out those zeros. Well, what made it 0? The x minus 4s. Those are going to factor out. So kind of a quick way, anytime you get 0 over 0, they have a common factor. You can cancel them out. Now, in pre-cal, we would say there is a hole at x equals 4, y equals 7. And that's what we would say. So let's take a look. Why don't we write 0 over 0? It's the equal to part. If I plug in a 3 here, I'm going to get 0 over 0. But this is kind of misleading. A function cannot ever equal something that we don't know what it is. A function can't equal an indeterminate. Because we don't know what it is. And if you say this, you're saying that this is a true statement, that a function can equal something that we don't know. And that's why it's very improper to write this. So if you write that, you're going to get it wrong. So be careful with that. So what's the correct way to do it? You have to show some work. And we're going to be doing this a lot this year. So we just want to get this out. Whoops. I know what y'all thinking. That should have been a 3 and not a 2. I apologize for that. Oh, nope. That should be a 2. Oh my gosh, this is embarrassing. This should have been the 2. There we go. We should be approaching 2. That's where we get the 0 over 0. So instead of a 3, we're going to make that a 2. I just noticed that my typo. So if we look at the top, we're going to get 0. Looking at the bottom, we also get 0. So again, this is our 0 over 0. We're not going to write it. We're not even going to show it on the paper. We're not going to write 0 over 0 anywhere because they're going to mark it out, take a point off. That's how they roll. But now what can I do is I can factor. The bottom is a difference of cubes. X minus 2, x squared plus 2x minus, or plus 2, sorry about that. So here's if you need help, here they are, cubes. X cubed minus y cubed becomes x minus y, x squared plus xy plus y squared, x squared plus y cubed is equal to x plus y, x squared minus xy plus y squared. There we go. And these 2's all cancel, and I'm going to get 1 over 8 if you verify that. So remember, in pre-cal, we're saying that there's a hole at the point 2, 1/8. All right, let's try the next one. Again, if I plug in the 0, I'm going to get 0 on top, and I'm going to get 0 on bottom. But we do not write that. Don't even do this. Don't even do that. That would be marked wrong also on the AP. You have to rewrite it. I don't know why they do it, but they want you to. 2 to the x minus 1 is 0, and the bottom as well. And we're going to be doing this a lot throughout the year, so we just want to get habit, making sure we're doing it correctly. Now, I do have 0 on top. There's my top, and there's my bottom. So how do I solve it? Well, I am going to factor. The bottom is a difference of squares. So remember, for difference of squares, a squared minus b squared is a plus b, a minus b if you need that. So I can factor, rewrite out your limit, 2 to the x minus 1, and on the bottom, let me make it a little bit better here, minus 1, I'm going to get 2 to the x plus 1, 2 to the x minus 1. And those cancel. Top, I get 1. On the bottom, if I plug in the 0, 2 to the 0 is 1, 1 plus 1 is 2. So again, we're saying x cannot be 0, so x the value does not exist. So we can say that f of 0 does not exist. But what are we approaching instead? And that's all we're looking to find. What it is we are, that looks terrible. So we are looking to find what is it we are approaching, not what the value will equal, because there's going to be a hole there, but what are we approaching? Because the value itself does not exist. We're just saying, what are we approaching? All right, the next method is the conjugate method. This is what we typically do when we see a radical. We multiply the numerator and the denominator by the conjugate. This will most of the time create a common factor that will cancel. So let's try this one. If I try plugging it in, I'm going to get the limit as x approaches 4 of root x minus 2 is 0. On the bottom, also equals 0. So I can't factor this one so well. So what am I going to do now? I'm just going to do the conjugate. And all that does is you're going to multiply top and bottom by the square root, by the conjugate of the numerator. So remember, the conjugate says if it's a plus b, we get a minus b. I do the same for the bottom. Now, a little hint, we never multiply at the bottom. The top is just going to become, what we've created is a difference of squares on top. So I know this is just going to be x plus 2 root x minus 2 root x minus 4 all over, and leave the bottom alone. We're not going to touch the bottom. Those cancel, the x's cancel, and I'm left with x minus 4, which will cancel with that bottom one. And if you clean it up, again, write out your limit. Anytime you rewrite a limit, you got to write it. 1 over the square root of x plus 2, and if you plug in the 4 now, we just get 1/4. Now, would we use the conjugate for this technique, for this one? So let's take a look. Well, check the top. The limit as x approaches 3, I do get root 3 minus 3, which is 0, but you look at the bottom. X plus 3 becomes 6. This is not indeterminate. So therefore, there is no technique, therefore no conjugate. So you might be asking, well, what's the answer going to be? And this is always what scares people, students. Well, it's okay to have 0. 0 divided by 6 is just 0. That's not indeterminate. 0 divided by anything is just 0, except for 0, of course. There we go. All right. So let's take a look at some fun ones here, some specials, okay? Ready? The first one, the limit as x approaches 0 of 1/2 over 1 plus 1 plus x, x plus 2 over x. So I'm going to check it. The limit as x approaches 0, looking at the top, I'm checking substitution first. And I do get 0 if you plug 0 in. Check a look at the bottom. Also 0. So this is indeterminate. So how do I solve this one? I'm going to use the least common denominator. So if I look at all the fractions here, the 2, the x plus 2, this is x over 1. I don't have to worry much about that. I'm just looking at my denominators. And that's my LCD. 2 times x plus 2. I am going to multiply the top and the bottom by that. This is the LCD technique. We're going to see this a lot. It's a really cool algebra trick. 2 times x plus 2. And if we rewrite it, we would get the limit as x approaches 0. When I distribute my common denominator, the 2's here will cancel out. And what I'm left with is just this x plus 2. Minus, but now I have to distribute this 2 times x plus 2 to the second term. In this case, the x plus 2's cancel, and I'm left with this 1, this 1 times that 2. Now, on the bottom, I can't cancel anything, so it's just that really long bottom. X times 2 times x plus 2. And if I simplify this, on top here, these are 2's, they'll just cancel. I'm left with x over x times 2 times x plus 2. And those x's will also cancel. The top is just 1, and if I plug in my 0, we just get 2 times 2, which is 4. We get 1/4. A very cool technique right there. We're gonna see this skill later on when we do the definition of the derivative. So that's a good skill to know. All right, let's take a look here. Now let's have some fun. What happens to the sign of 1 over x as x goes to infinity? So let's think about what sine of x does as it goes to infinity. If you look at sine of x as it goes forever, it just oscillates, right? It oscillates. So therefore, sine of x approaches is, so if we would take the look at the limit there, the limit as x approaches infinity of sine of x, we would get a d and e. We'll talk about that too, okay? We just get d and e because it's just oscillating. It's going on and on and on. It's always repeating itself. So sine of x just gives me a d and e. But what happens if we have 1 over sine of 1 over x? Well, so let's take a look at this. This is sometimes what we use like an inside rule, like your composite function. Look at the inside. The limit as x approaches infinity of 1 over x. Well, this is an interesting little thought for us. What happens as x goes to infinity? Well, x gets really large. Now take a number, any number divided by a really large number. Take 5, divided by like a billion. It's basically 0. So we know that this is just 0. As a matter of fact, this is going to become a rule for us. So if I know the inside is just approaching 0, I'm really saying, well, the outside one is now approaching 0. So another way to think about this is just sine of 0, because the inside here is just becoming 0. And what's the sign of 0? Just 0, right there. So there's the answer. So that whole limit is just approaching 0. All right, what about this one? Let's try this one. Infinity is kind of easy to work with. Plug in infinity squared. What do you get? I get infinity squared. Don't ever write this, okay? We're not going to write this, but we can think it. Infinity squared plus infinity. Well, if you take infinity squared and you add infinity to it, what do you get? Infinity. That's it. Now, again, we're not going to ever write that because it's really improper to say what anything times infinity is infinity because it's not really true. Like if I said 2 times infinity, well, let me take a look down here real quick. Let me show you some things. Let's show you some things here. So, hint. Always check for substitution first. Substitution is easy to work with, and if we don't have to do any of the algebra stuff, it makes it much easier for us. But let's deal with infinity. Infinity is a weird concept for us. It doesn't exist. Infinity does not exist. Try counting to it. I tried once. It took forever. So how do we work with infinity? Well, if I say, what is 2 times infinity? Well, we know it's going to be infinity, but this is what we call improper. We don't like to say infinity times infinity because it's improper to write that. Because you're taking something that does exist and you're going to multiply it by something that does not exist. How do you get something if you can't do it? The math is impossible. You can't take something that does exist and multiply by something that does not exist. So what is the proper way? And we only do this in our head. What's the proper way? Well, if I would say 2 times x. I would say, what's the limit as x approaches infinity of 2x is infinity? It's not because 2 times infinity is not infinity because you can't equal infinity. You cannot equal infinity because you can't get to it. You can only approach infinity. So when we're dealing with infinity, we got to be really careful about the semantics. Now, what do we all do in our head? If I said what's infinity squared, you would all say, of course, infinity. And our brains can handle it. Our brains can handle infinity. But mathematically, it's improper to work like that. We tend to think of them as limits. Give it to you graphically. Let's imagine we have a graph. Here's my x-axis, here's my y-axis. Where's infinity on this graph? I've had students say, well, there's infinity, Mr. Warnow. But what does this imply? That there are numbers greater than infinity. And that's not true. Because infinity, by definition, is the greatest number possible. So you can't have anything out there. Well, often you say, well, can I just put it on the end of a number line? I reckon you can, but it's still not the best way to represent it, because if I'm graphing, we're kind of giving infinity some sort of height, which would be improper. So infinity does not exist in our real world. It doesn't even exist in the universe. We always say the universe is infinite. It's not. It's finite. We just don't know where it ends. That's the definition of infinity. We don't know where it ends. So we don't know anything about it. So that's why it's very important to know the difference between proper and improper ways to deal with it. And that's what's going to help us here, because a lot of it we can just do in our head. So, for example, something like this one, I might say, okay, the limit as x approaches infinity, let's do cosine of 1 over x. Well, again, this is approaching 0. I can do that. I know as x gets really large, that gets closer to 0. And what am I left with? I'm left with the cosine of 0, which is just 1. So so this is approaching 1. It's not going to equal 1. We're only approaching 1. All right. Hope you guys enjoyed the video. I'll see y'all later.